Hello students, we are in fourth example of chapter 10 wave optics. A few questions we are given. What is the effect on the interference fringes in Young's double slit experiment due to each of the following operations? Very first operation is the screen is moved away from the plane of the slits. So in Young's double slit experiment we have this type of situation where we place two sources, say S1 and S2. Let them be at distance small d. Screen is placed at capital D distance, and let this be the reference line. We'll call this point S if needed to address it, and this one O. Now, the question is screen is moved away, and what is the effect on interference pattern? You move the screen and you are not making any change here. So the angular separation of the uh, angle, angular separation of the fringes will not change, but we know that x by d is equal to path difference by lambda. Okay, now path difference we are not making any change in, but as you are changing capital D, so what difference does it make? You are changing x, means more the d more the x is directly proportional to capital D. In this case other parameters are constant, and hence fringes will be separated more, width of the fringe will be more. Okay, so what you can say is fringe width will increase, angular separation will not change, it will remain same. That is a. Second one, the monochromatic source is replaced by another monochromatic source of shorter wavelength. Now again, I would go by same formula. Look at the formula. X by D is equal to path difference by lambda. So capital D and path difference are constant. So X is, sorry, I'm making one mistake here. It's not lambda, it is small d here. Okay, so now small d is the separation of the slits of the two sources, and it is constant in second question. Screen is also not moved, so I can say that x bar is directly proportional to path difference, and x bar is directly proportional to lambda. So when you change lambda, if you decrease lambda, what will happen? X decreases. X decreases means fringes will be more crowded. Fringe width will decrease, fringes will be more crowded. Going to third one, the separation between the two slits is increased. Again, the same formula will help us. I am not writing it again. Go to this formula again. Which parameter now we are changing? We are changing D. And what is the relation? X is proportional to 1 by D. So the separation between the two slits is increased. If you increase D, X will decrease. X will decrease means fringes will be more crowded. Fringe width will decrease. Fringes will be more crowded. Next one. The source slit is moved closer to the double slit plane. What does it mean? See, behind S1 and S2, we keep one source. So from this source, we are taking wave fronts, and source is placed in such a way that part of same wavefront enters through S1 and S2. Now, when you bring this source close to S1, S2 plane, at that time you are not sure whether same wavefront is passing through S1, S2. So one possibility is fringes may disappear. Second possibility is the brightness of the fringe may alter. So these are the two possibilities, and if you place source very close to S1, S2, it may be possible that fringes uh, may vanish totally. Next one, the width of the source slit is increased. What does it mean? What we are doing here is, what if you increase this width? If you increase that width, you are sending more intensity, then the brightness of the uh, construct interference, bright fringe, will be more. And lastly, the monochromatic source is replaced by source of white light. So when you are sending white light, you are sending so many wavelengths, so many different wavelengths, and then you will not be able to recognize between bright and dark fringe, because different wavelengths will produce bright fringe at different distance, which may be overlapping with dark of other wavelength. So overall, there will not be any interference pattern. Thank you.